Today we're going to talk about saddle point asymptotics, which is where we turn to estimate coefficients for generating functions that have no singularity. This is the final step in complex asymptotics. It's the last way to get a quick asymptotic estimate of generating function coefficients according to our standard overview. To understand saddle point, we need to talk about modulus surfaces. And this is a three-dimensional extension of what we've been using in 2 dimensions. And to warm up, I just want to look at 2-dimensional plots of functions where we plot x versus the absolute value of some function of x in a Cartesian plot. So for example, the function 2x is just a line, but absolute value of 2x is a v. When it hits 0, it bounces back up again. Or 1 over x, it's a familiar hyperbola, but absolute value of 1 over x is a little inverted funnel. Sine x goes up and down. Absolute value of sine x keeps bouncing off the origin. 1 minus x squared is a parabola, but the absolute value of 1 minus x squared starts to look a bit like Batman. And as we get to more complicated functions, we get more interesting shapes. So this is a cubic, for example. And I just bring these up in 2 dimensions so that the shapes that we see in 3 dimensions are not quite so jarring and can be interpreted in terms of shapes like this. So now what we want to do is look at 3-dimensional versions of the plots of analytic functions that we've been working with. Those things are called modular surfaces, which is a plot of x, y, and absolute value of some function, where x and y are points in the Cartesian plane that correspond to x plus yi. And we've been using plots like this to help us identify poles and understand the topography of the poles in complex functions already. For example, here's a plot of 1 plus 4z squared over 1 minus 4z squared, where black corresponds, the blacker a point is, the higher the absolute value of the function. And so with a plot like this, we can see at z equals plus a half and minus a half, where the denominator vanishes. As we get closer to those points, the value of absolute value of f of z gets bigger and bigger. Where the near 2i, I over 2 and minus I over 2, where the numerator goes to 0, then it gets to be white. But now in 3 dimensions, this plot has a much more fascinating shape. So this is the same plot in 3D. And we'll be looking at properties of plots like this called modulus surface to help understand the saddle point method. So one of the first questions come up is, can we get any shape this way? One interesting aspect of these kind of plots is that no, actually the shapes that we get are very highly constrained by the situation. In fact, there's only 4 different types of points on these kinds of surfaces. There's zeros, where the thing actually does get to 0. The absolute value of the function actually gets to 0. So in this case, that's I over 2 minus I over 2. There's ordinary points, which is pretty much everything else, where these things are very smooth. And it's not surprising they're smooth, because analytic functions are smooth. They're infinitely differentiable where they're defined. And then there's poles, which we've already talked about. And then there's a 4th type of point called the saddle point, and that's what we're going to focus on in this lecture. Okay, so let's go through these types of points one at a time. So the first one is zeros. And we'll first talk about simple zeros. That's where the function is 0 and the derivative's not 0. So this is a typical example of a modular plot of a function, simple function showing off a 0. So this function is f of z equals 2z. So in polar coordinates, that's 2r e to the I theta. But the modulus is always 2r. So it doesn't depend on theta. So that means if we go out a distance r, then we're going to go up 2r, and then we'll have a circle, so it's a cone. So it's the same for all theta, and then it comes down to a point right where at 0, where f of z equals 0. So that's a typical 0. Now what's interesting is that all zeros kind of look like this. They have the same local behavior. That's because an analytic function we can expand using Taylor's theorem in terms of its derivatives. So we can write at any point f of z equals f of z0 plus f prime of z0 times z minus z0 and so forth. And then if it's a 0, then the first term is 0 and the second one is a constant that's not 0. And then after that, as we get closer to, as z gets closer to z0, then it behaves just like that constant times z minus z0, just a linear function. So just like this. They all have the same local behavior. And that it also doesn't depend on theta. So for example, here's a function that has two zeros, 1 minus z squared. So you can see, looking at the profile of it, it looks kind of like our Batman parabola, where it bounces off the axis and goes up. But around the zeros, it's little points like this, because it has the same local behavior as a simple 0 at the 2 points plus and minus 1. That's just doing the math to show the functions that it behaves like locally. And then, so if we take 1 minus z cubed, then we have 3 roots, or 1 minus z to the 8th, we have 8 roots and so forth. These surfaces look quite intricate and complicated, but actually all they are is collections of these points that go down to the zeros. So now that's a so-called simple 0. If you have a point where the derivatives are 0 for a while, and then finally there's a place where some derivative is non-zero, that's called a 0 of order p. So like z cubed has a 0 of order 3, so the point is curved a little bit more down at those zeros. And so for typical functions, you might have multiple types of zeros. So this is the function z squared plus z cubed, and then you can see the little profile of the cubic function there. One of the zeros is of order 1, the other one is of order 2. So it's fairly easy to understand what zeros are. Those are the points where it touches. And if it's of order 1, it's always going to be a point. Otherwise, it'll have a more rounded contour where it touches. So that's what zeros are like. Now there's poles. We've already talked about poles. A pole is a point where the function behaves like a constant over z minus z0. So as z gets close to z0, it blows up. So that's a typical pole, 1 over 1 minus z. And around the pole 1, again, it's going to be the same for all theta. So it looks like this chimney. And you can, if you cut a cross-section of that, then you get a cross-section of what we saw with the hyperbola in 2D absolute value land. And again, by definition, all poles have the same local behavior. So that's a function with 3 poles, 4, and so forth. This is just 1 over 1 minus z cubed, 4th, and so forth. 1 minus z to the 25th. So again, interesting contours tying together poles. But locally, they all behave the same way. And also you can have poles of order p, as we know, where the function grows like a constant over z minus z0 to the p. And those are just chimneys that are tighter and go up faster. So that's what poles look like in a modulus surface. So here's just a quick exercise. What function is this? So this is a function that's got 1 0 and 1 pole. Well, this is a really easy function. It's z over 1 minus z. So there's a pole at 1 and a 0 at 0. And then the rest of the surface is just integrating that together. Z over 1 minus z. And think about the 2D analog to that if you want to think about what the cross-section is like. And so we're going to see variations on this kind of surface for all different types of functions. But now there's the two other types of points. Well, first one is ordinary points. So that's a point where the function's not 0 and the derivative's not 0. So neither one of them is 0. And that's just places where the function is smooth. And again, all ordinary points have the same local behavior. If you look at the expansion as z approaches z0 around any point z0, then what's going to dominate is just the constant, the f of z0. And the rest of the terms will go away as we get closer and closer to z0. It's just an indication that it's smooth. But now we come to saddle points, and that's the kind of new idea. And so a saddle point is a point where the function's not 0, but the derivative is 0. So here's a plot of the function 1 over 1 minus z times 2 minus z. So it's got poles at 1 and at 2. Now all saddle points have the same local behavior, just as for poles and zeros. And again, if we write out the Taylor expansion, now in this case, the function f of z is non-zero, but the derivative is 0. So what that leaves is a quadratic term, and that's the term that's going to dominate. So the idea of a saddle point is that there's parabolas, and it does depend on the angle. So at one angle, there's going to be a downward pointed parabola, and at another angle, there's going to be perpendicular to that. Actually, there's going to be an upward pointed parabola. And if you take cross sections all around, it converts from one to the other. But the behavior is always quadratic. It's got a parabola. That's the basic characteristic of saddle points. And that's just like a saddle. That's where the name comes from. You got a downward parabola and an upward parabola. And we're going to take advantage of that key characteristic of saddle points to estimate coefficients in generating functions. So here's a quick summary. This is a modular surface, and we talked about the 4 different types of points. So there's simple zeros, where the function is 0, but the first derivative is not 0. And this one's got its simple zeros as indicated. Then there's zeros of order p bigger than 1. We don't have one of those in those. That's where the curve goes down. Then there's the saddle point, where the function is not 0, but the derivative is 0, and it behaves like a quadratic function. And then there's ordinary points where neither the function or its derivative are 0. And that's most points in the surface. And then there's poles where it blows up and is proportional to a constant over z minus z0. But the key thing to note about this table is, and that's where the function or its derivatives are not defined. The key thing to note about this table is that covers all the possibilities. Either they're both 0, or the function is 0, derivative is not, or the function is not 0 and the derivative is, or neither one of them is 0. That's all the possibilities. Those are the 4 types of points. And indeed, there's what's called the maximum, that's an expression of what's called the maximum modulus principle, and there's all kinds of implications from that. For example, there's no local maxima in a modulus surface. There's nothing that looks like an upside down parabolic mountain. Everything either blows up or it touches down, and then there's saddle points which are in between these, but that's the characteristic of these surfaces. So just with that summary, we can just finish by taking a look at, well, first of all, how do you find the saddle points? So here's a simple example, 1 plus z squared plus z cubed. Where are the saddle points in this modulus surface? It's easy to know where the zeros are. That's where the thing equals 0. Where's the saddle points? The definition of where the saddle point is where the derivative is equal to 0. So derivative of that is 1 plus 2z plus 3z squared. You set that equal to 0 and solve it, and you find that the saddle points are at minus 1/3 plus or minus I square root of 2 over 3. Minus 1/3 in, and then square root of 2 over 3 on either side of the axis. If you look at a bottom view of the surface, you turn it upside down, you can see that that's where those points are, and that's the downward parabola. Well, in this case, it's the upward parabola upside down and the downward parabola upside down. So the zeros are at minus 1 and plus or minus I, and the saddle points are at minus 1/3 plus or minus I squared root of 2 over 3. It's easy to find saddle points. Set the derivative to 0, and the points at which the derivative is equal to 0 is where the saddle points are. So that's one of the important things that we're going to need to do in order to analyze generating functions with no singularities. So just to finish, here's some of the generating functions from analytic combinatorics that we've already looked at. So this is the type of generating function that we looked at for finding strings with no sequences of k consecutive zeros. This is 4 consecutive zeros. And we were looking at the plots showing us where the poles are, and if you look at the modulus surface, you got both the poles and the zeros, and that's the kind of shape that you get for a function like this. This is the one for generalized derangements, where we had this kind of plot, and it showed that this lonely pole is the one that's closest to the origin, and determining the asymptotic behavior, the modulus surface has a more striking characteristic, even more striking characteristic. This one is 1 over 2 minus E of z, and that's for generalized surjections, and that one's got poles kind of next to the imaginary axis. Again, the surface plot tells us it's the same information just presented in a different way. Now, all of these have singularities, and we were able to analyze behavior of coefficients because of the singularities. What we're going to do next is look at the functions that have no singularities and how we're going to estimate coefficients for those functions.